Let's talk about math, but forget dusty chalkboards for a second. Think of it more like a toolkit, you know? A collection of incredibly powerful, elegant tools for describing, predicting, and solving the puzzles of reality itself. So let's start with a really big question. From the way planets move to how information flows across the internet, our world follows certain rules. But how do you actually write those rules down in a way that we can understand and, more importantly, use? The answer? We use the language of mathematics. Every single formula we're going to look at today is like a perfectly crafted sentence in that language. It's a tool designed for a very specific job. So let's crack open that toolkit and see what's inside. Okay, our first compartment holds the tools for structure. These are the formulas that help us organize unbelievably complex information and figure out the three-dimensional world all around us. So imagine you're trying to manage a supply chain with hundreds of different variables, or maybe analyze a complex electrical circuit. You're staring at this massive web of interconnected equations. How on earth do you solve them all at once without losing your mind? Well, you use the matrix method. This brilliant formula lets us pack all of those equations into one single tidy statement. AX equals B. Here, A is just a grid holding all the fixed relationships in your system. Things like prices or connection strengths. B is your list of outcomes, and X, well, X is the whole set of unknowns you're trying to find. And with a little bit of algebra, we can isolate X, solving for everything in one clean shot. Now, the real magic here is finding something called the inverse of matrix A. And I know, it might look intimidating, but it really just boils down to a repeatable three-step recipe. First, you calculate a special number called the determinant, which basically tells you if a clean solution even exists. Then, you find a related matrix called the adjoint. Finally, you just combine them. The point isn't to memorize the steps, but to see that there's a reliable process for untangling even the messiest web of equations. Okay, let's switch gears a bit. We're moving from these abstract systems into the physical world. Think about a rocket launch or the forces acting on the bridge. These things have both a strength and a direction. So how do we capture both of those ideas in one single object? We use vectors. And to find the actual strength, or what we call the magnitude of that vector, we use this formula. If you remember the Pythagorean theorem for finding the long side of a triangle from school, this is really just the 3D version of that. It lets us figure out the true straight line length of our vector, giving us one single number to represent its total strength. But what if you have two different forces, and you need to know how much they're working together? That's where this little tool, the dot product, comes in. It's a super simple operation that tells you how much of one vector's force is pointing in the exact same direction as another. It connects the lengths of the vectors to the angle between them, and it's absolutely crucial for things like calculating the work done by a force. Basically, figuring out how much of your push is actually moving something forward. All right, let's move to our next compartment. We've handled static structures, but now we need the tools for a world that's constantly moving. This is the language of change. This is the heart of calculus, and it was a giant leap from the static world of geometry to a dynamic description of reality. So before we can analyze change, our functions need to be, let's say, well-behaved. A continuous function is simple. It's one you can draw without ever lifting your pen from the paper. But for calculus, we usually need something even better, a differentiable function. This just means the function isn't only connected, but it's also perfectly smooth. No sharp corners. Think of a smooth roller coaster track versus one with sudden jarring turns. We need the smooth one. Once we have a smooth function, we can pull out our next tool, differentiation. You can think of this as our precision speedometer. It doesn't just give you an average speed over a whole trip, it tells you the exact rate of change, the slope, at any single instant in time. Of course, functions in the real world can get pretty complex, so our toolkit has specialized rules for that. If you've got two changing things multiplied together, the product rule tells you how to handle it. If you've got a function nested inside another one, kind of like those Russian dolls, the chain rule lets you peel back the layers one at a time. You don't need to memorize what's on screen, just know that we have reliable ways to figure out the rate of change for even the most complicated systems. Okay, so we've got the tools to measure change. Now what? What can we do with that? Well, in this section, we'll see how to apply that knowledge to solve some really cool problems. And then we'll learn how to do the entire process in reverse. This is the real power of the derivative in a nutshell. Just by looking at its sign, we instantly know what our original function is doing. If the derivative, the slope, is positive, hey, the function's increasing. If it's negative, the function's decreasing. It's a super simple, immediate insight into the trend of any system. So think about that. If a positive slope means you're going up, and a negative slope means you're going down, what happens right at the very peak of a hill or the bottom of a valley? The slope is perfectly flat, right? It's zero. And this gives us this incredibly powerful tool for optimization. If you want to find the maximum or minimum of anything, from a company's profits to the efficiency of an engine, you just find the spot where its rate of change is zero. Okay, now let's put that speedometer in reverse. If differentiation is all about breaking things down into a single instant, then integration is about adding all those infinite little instances back up again to get the whole picture. It's the totalizer in our toolkit. The most intuitive way to think about this is finding the area under a curve. Integration lets us slice that area up into an infinite number of tiny, tiny little rectangles and then sum them all up perfectly. It gives us a precise total area, even for the weirdest, most complex shapes. And what if we want to find the total amount of something, not over the whole function, but just between two specific points, A and B? We use what's called definite integration. This formula lets us calculate the exact net change between a starting point and an ending point. For example, if you knew the velocity of a rocket at every single second, this formula could tell you the total distance it traveled between, say, 30 and 60 seconds after launch. And this is where our whole toolkit really comes together. We can start with an equation that only describes the rate of change. Like, say, we know a population's growth is proportional to its current size. By using a clever trick to separate the variables and then integrating both sides, we can essentially work backward from the rate of change to find the original function that describes the population at any given time. It's amazing. All right, for our final compartment, we're going to turn to a world that isn't always smooth and predictable. This is the toolkit for navigating uncertainty, for making logical decisions when we don't have all the facts. Here's the central question. You know that one thing has happened. How does that new piece of information change the likelihood of something else happening? And this isn't just a thought experiment. It's the core logic behind medical testing, weather forecasting, you name it. And the tool for this is the formula for conditional probability. It gives us a precise mathematical way to update our beliefs when we get new evidence. It just says the probability of event A, given that B has already happened, is the probability of them both happening, divided by the probability of B all by itself. This is the engine of rational prediction. So, there you have it. We've seen how matrices can organize these vast systems, how vectors describe physical forces, how calculus gives us the language of motion and optimization, and how probability lets us reason our way through uncertainty. See, this isn't just a list of formulas, it's a toolkit for thinking. These are the instruments that let us write down the rules of reality, and in doing that, to understand it and to shape it. So the only question left is, what problem will you solve?